Yesterday, we introduced the idea of calculus as putting infinity into all of our math, trying to rigorously understand what is going on with this infinity business. This has to do with studying calculus as the mathematics of studying how things are changing. But really, the new rigorous thing that we come up with in calculus is this infinity business. And how is this supposed to work? One of the central tensions that comes along in calculus is the distinction between the discrete and the continuous. Because what we're trying to do is model the continuous with the discrete. And we have to know when we can do that, how we can do that, and what we have to think about. What are we just waving our hands at when we do this? And our framing device for this is the standard beginning of calculus, the two big questions of calculus. What's the slope of the line tangent to a function at a given point? And what is the area under a curve and above an interval? These stay the two big questions of calculus for the rest of calculus. So this semester, we're going to be focused mostly on this area under the curve business. And as it happens, things that we can do with area under a curve. Just like in Calc 1, we've concerned ourselves with the slope of the tangent line business and the things that we could do with the slope of the tangent line business. Next semester, when you go into Calc 3, you're going to be dealing with multivariable calculus and vector calculus, and we're going to be concerned with the same two big questions. We're going to have to modify things because our functions are no longer going to represent one-dimensional curves in two-dimensional space, but the questions are going to be the same. We're going to modify them to fit our new functions of two variables or equations in more than two variables. Let's talk about this area under the curve business. This is the important part of what we're going to look at next. We know we have lots of formulas for area. Area of a square, area of a rectangle, area of a triangle, area of a circle, area of a trapezoid. No one ever knows that one, but that's okay, because the only area formula that we need is our base definition of what area is. It's length times width. Because we are empowered with calculus, we do not need anything but length times width. The only area we need is the one that defines what area is. Area is length times width. Area is multiplication. Looking forward, when we start to want to apply integration, the applications of integration are going to be the same as the applications of multiplication. So if you don't know what integration is for, that's also kind of means that you don't know what multiplication is for. But you do know what multiplication is for, so you do know what integration is for. Let's see what we mean by this. The way I like to think about integration is that integration is multiplication, but one of the factors is continuously variable. That's our baseline. Integration is multiplication but one of the factors is continuously variable. Integration is multiplication, but one of the factors is continuously variable. Two problems with this: variable and continuously variable. We have to deal with both of those things. Multiplication is addition where all the terms are the same. So we got to think about this multiplication business. Multiplication is our shortcut to addition when everything is the same. Multiplication is addition when all the terms are the same. So if I have an addition problem that says 5 plus 5 plus 5, we notice that all of our terms are the same. So we get to use multiplication. Let's summarize this by saying 3 times 5. If the terms aren't the same, then we're stuck with addition. If the terms aren't the same, then we're stuck with addition. So if we have 3 plus 4 plus 5, there's 3 terms, but they're not the same, so we don't get to use multiplication. I can't say this is 3 of one thing. So we just add. Let's see what this means in terms of a continuously variable sum. We're going to draw a picture of each of these. So this first one, where the addition, the multiplication is addition where the terms are all the same. We're just going to draw a picture where it's always 5. I can only barely see the dots. So in this picture, I kept getting distracted because I drew this way too big. In this picture, we want to find the area. And this area we find just by multiplying 3 by 5. Our height, our length is always 5. We just get to multiply that by the width. So in this picture, length is always 5. We calculate the area with multiplication. How's everybody okay? Everybody looks stunned. You all look like this. But that's kind of because it's 8 o'clock in the morning and you're in a math class. In the second case, we want to, our terms are not going to be all the same. We had three different terms. We had a 3, a 4, and a 5, and each of those was being used once. So we have a 3, a 4, and a 5. Our length was variable. So we didn't get to use multiplication over the whole width. We had to use addition. So we had these three different values for the length. The length was variable, but the length was not continuously variable. So now we enter the integration side of things. In this one, we get to use addition. In the first example, we got to use multiplication because nothing was changing. Second one, things were changing. We had to switch up to addition, but now we're going to switch to continuously variable. Well, I've already not switched colors. So in this last example, the height is being defined by the function f of x, and that function is continuously variable. The length is continuously variable. In the previous example, our first height was 3, the next height was 4. Our first length was 3, the next length was 4, the next length was 5. In this example over here, I want to find the area under the curve. The first height is f at a, whatever that height is. There is no next height because the height is continuously variable. So here we could say the first height is 3. I've been saying length. First length is 3. And we can just move on to the next length is 4. We have a place to put a plus sign. In this example, our first height, our first length is f at a. But there is no next length because the length is continuously variable. So that's the setup. That's the idea. This is the thinking behind integration. Integration is multiplication, but one of the factors is continuously variable. This means that integration is addition, but it's going to be some weird addition because there's nowhere to put the plus sign. In this example, there's a place to put the plus sign, nowhere to put the plus sign. Any questions? How's everyone okay? That would be the end of like the next TikTok. I'm off to speed it up. 8 o'clock, I have a multiplier of like 0.7. Normally I talk kind of fast, but at 8 o'clock in the morning, it's like everything is like going through like, it's just like it's just like an increased viscosity that I feel like I have to move through. I don't know if it's because I haven't delivered enough coffee to my system. Full disclosure, I am a drug addict. It's just one of the mild drugs that no one cares about. Everybody's like all on one hand cycle. Oh, disgusting drug addicts. Ew. And then the very next thing is like, oh, I can't get by without my coffee in the morning. You know what I mean? I'm not trying to make an equivalent between heroin and coffee because no one who was trying to wake up and do stuff would take heroin in the morning. It's not like a wake up and shoot heroin kind of thing. You know what I mean? It's like, oh, ooh, I got to get going. That's like, the answer is not heroin. It's cocaine. I'm just kidding. I grew up in the 80s. I get to make that joke. So this is what we're basing our thinking on. We're just trying to do integration with multiplication, but one of the factors is continuously variable. Right now, this is what is called downtime. We were just talking about some stuff. I have to stop talking about stuff. Talk about something that's distinctly not math to punctuate the few minutes of math that we have. It can't be all math all the time. It just turns into a Michael Bay movie, like one of the action sequences in a Michael Bay movie, where no one can tell what the F is going on because there's too much happening, right? So you have to have a scene. It's like an action scene. And then you have to stop. And the characters have to do something calm for a while. Since it's a Michael Bay movie, they just do exposition for why the next action sequence is going to happen. I mean, it's not like storytelling. It's just like filling time to the next action sequence. It's that D&D campaign where you just set up one fight and then you just wait to set up the next fight. The only thing that's happening is like there's a hallway. Are there any traps in the hallway? No, the point is the fight at the other end of the hallway. It's like a modern first-person shooter game now. This is a cutscene. By video editing skills, I'd be chopping this up, adding some music, Music is important. It tells us how we're supposed to feel about a scene, because the writers aren't writing scenes where you can tell how you're supposed to feel. Like the actors are up on the screen saying shit, and you're like, oh, what are they talking about? And then sad music starts, like, oh, they must be talking about something sad. Okay, I'll be sad. Oh, it's tense music. Okay, I'll be tense. This is a math class. And so I like to use the silence for the emptiness that we feel inside. Most of you are trying to become engineers. That's usually what people are doing when they take this class. So you really got to start practicing that dead, empty feeling inside. Because you got to find a workplace that's going to ask you to work like 170 hours per week. You're going to be an engineer, so you're going to know that there are only 168 hours in it. So some of those are going to be overtime. But since you're a salaried employee, they aren't going to care. They're just going to say, no, we're trying to build something important. And you're like, well, yes, we're trying to build something important. So you guys have to work always. We've installed some desks for you in the open workspace, and the desks conveniently have a hammock underneath, so you could just sleep here. I don't know if you know this, but does anybody know anybody that works at Genentech? At Genentech, they have a concierge. So if you need to have like dry cleaning done, you can get that done at work. If you have a haircut, get that done at work. If you need someone to go out and pick something up, they'll do that for you. And it seems like it's a nice thing, right? It's like, well, we're helping you out. It's so fucking dystopian. It drives me crazy. It's like, oh, no, you may not leave. We'll take care of that for you. Stay here and work. Anyway. Better than some of the alternatives. Let's deal with this continuously part of continuously variable. Pause for the start of the next video as if I'm ever going to edit this. Let's deal with the continuously part of this continuously variable. All we're going to do is take that continuously variable case and drop it back down to just plain variable case. We're going to assume that the function is constant in short bursts. That's how we drop back to the previous case. So our strategy is we're going to drop back to the previous case. Drop back to just variable by assuming that the function is constant in short bursts. We're going to drop back to just plain variable by assuming that the function is constant in short bursts. This will allow us to use multiplication on the short bursts and give us a place to put the plus signs. So this does a couple of things for us. We get to use multiplication on each short burst, and we have a place to put the plus signs. Let's draw a picture of what we want to accomplish, of what we're doing. So we've got some function. Doesn't have to be a function. Notice I bailed on function and wrote curve. And I bailed on the fancy terminology constant and just referred to it as flat. I'm also going to draw something with a little less flair. I just turned it right into a function. It's a function. It's fine. It's fine. So what we're going to do is take this super fancy curve and drop the resolution on it. Right now, we're at PS5. And we're just going to drop back to Game Boy. So we're just going to flatten everything out. Why'd you drop so big? So that you have 5. You could have just had 3. There we go. We're just going to lower the resolution. We're not that far off. It's close. We can see the part that we're missing here. We can see that I'm shading in almost all the area under the curve. But the benefit is now on each of, I've just drawn this area with this inconvenient continuously variable length. And I've just picked 5 lengths. On each of these rectangles, we get to use multiplication, and we just put plus signs in between each of those areas. Need to write that down. I just said it. I didn't write down a notation for this anyway. Any questions? So this will give us an approximation. We have these 5 areas, A1 plus A2 plus A3 plus A4 plus A5. And on each of these areas, we get to use multiplication, because on each area we've flattened out the function. So we get to use length times width. Now, when we make an approximation method, we have to come up with how to improve the approximation. And in this case, we'll just use shorter bursts to improve the approximation. So what if I did twice as many? So notice that now that I've gone up to 10 rectangles to approximate this area, I've included a lot of that missing space. Here's some extra space that I didn't have before that I have now. Here's some area I didn't have before that we have now. More rectangles gave us a better approximation. More rectangles means a better approximation. Now we have to think about what calculus has to say about this improvement. How can we improve this? If we use more rectangles, we get an improvement. So how many rectangles should we use? Infinitely many rectangles. That's the calculus way. Find a way to improve your approximation. And just think about what happens if I do this forever. How's everybody okay? That'll be the end of the next second video. Stay tuned for part 3. Trying to compartmentalize stuff. You can tell I'm compartmentalizing stuff. I'm putting a period on this by having a commercial break right now. I used to do class with just regular commercial breaks, but modern audience is not going to accept commercial breaks. Does anybody watch commercials anymore? I don't watch commercials anymore. I don't watch a show unless it's been recorded. Who watches a show live? I'm not going to let some TV station decide when I'm going to watch an entire season of a show. No, you have to watch 1 hour increments and you have to wait a week between. It's like, oh, no, I don't. I'm just going to record that shit and watch it all at once. And also fast forward through all the commercials. They're like, oh, but that's how we pay for this. I'm like, oh, fuck that. I'm already paying for the TV service and now I have to pay for the commercials? Nah. No. Then these giant media conglomerates are like, oh, well, how are we going to make money? I'm like, oh, that sounds like a you problem, not a me problem. I mean, seriously. Like when you go to the grocery store, it's like, hey, do you want to donate $1? It's like, oh, no, I'm just some person. You're the billion-dollar corporation. Why don't you donate a couple $billion? Tell you what, instead of a tax, instead of a charity, how about we just collect it in a tax instead of you just funneling it offshore and putting that money to sleep? You know what I mean? I guess what I'm saying is that Jeff Bezos isn't a job creator. Every single person in here that's working, how many of you here are working and not saving money? How many of you here have a majority of your money go out to just existing, paying your rent, buying food, paying for this? I don't know. If you don't have disposable income, I don't know why you're disposing it on this, but that's not for me to judge. That's fine. But if you're spending a lot of your money every month, you're creating more jobs. You're making the economy go. Money moving is the fucking economy. Money being put to sleep offshore. I'm looking at you, Apple. Money being put to sleep offshore, that stagnates the economy. That's ours. We built that. Let's go get it back. You know what I mean? Well, we're like, oh no, I really like my iPhone. You can like your iPhone. I fucking love my iPhone. Like to an unhealthy degree, I think. And clearly, I'm not getting paid for this advertisement. They just stuck that on my goddamn computer that I happen to have in front of me when I'm working so that you could be, oh, Leach is some kind of Apple guy. I don't really care. I just wanted the Toyota Camry of computers. You know what I mean? It's like, oh, you can get much more performance out of it, out of a computer, like a PC. You can build your own. It's like, well, that is true, but I don't want to do that with my computer. I just want the shit to work. You know what I mean? It's like, don't make fun of people for buying a RAV4. RAV4 is the rational choice. If you're a car enthusiast, it's gonna suck, right? I don't know if you're any car enthusiasts here, but if you're a car enthusiast, you're not gonna be happy with a RAV4. But most people aren't gonna be happy under the hood of their car every weekend because they're gonna try to squeeze out 3 more pounds of boost and have their engine blow up on a semi-regular basis. You know what I mean? Anyway, I like Apple products, but come on, company, be better. All right. I think it's not so much that I didn't want to go to commercial breaks. I just decided I had complete editorial control over the commercial breaks. So I'm just going to talk about shit for a little while. Try to find someone that disagrees with me so we can have a conversation and possibly make progress. But no, we're not really interested in conversation. We're not interested. No one is interested in a debate. Anybody that asks for a debate is not interested in debate. They just want to dunk on people. It's like those Facebook memes where it's like, what's the order of operations? It's just, people are just trying to cause fights. People just stirring shit up. Don't fall for that. Someone posts one of those things like, oh, can you solve it? Michael, it's not an equation. Can you simplify it, first of all? But then you're kind of being a dick about the grammar. But that's beside the point. Just block that person. They want you to start a fight with your friends. Call your friends, say, don't respond to this. And whoever posted it, block that person. I'm not talking about just on Facebook or Instagram or social media. Block that person IRL. They like walk into the room, it's like, oh, did you see that meme that I posted? Klingon discommodation. Turn your back and fold your arms. I mean, just like that episode where they ignored Cartman. Just do that. Because look how successful that was. I know it led to some crazy hijinks, but it'll work. All right. So we're going to deal with the continuously parts of this continuously variable by dropping back to just plain old variable by assuming the curve is flat in short bursts. This gives us an approximation of the area under the curve, an approximation that we improve by using more rectangles. So the natural conclusion, calculus-wise, is to use an infinite number of rectangles. We need some notation to go along with this. In our first 5 rectangle setup, we had these widths of delta x. I'm just going to say some small change in x. This is the same kind of delta x that we had yesterday when we were calculating slope, delta y over delta x. And the same thing is going to be happening. We had delta y over delta x. As the points got close together, we are getting close to something that looks like 0 over 0. And the same thing is happening here. In the previous one, it was in the slope version, it was like, oh, what 0 over 0 are we headed towards? That was the question. We couldn't just go to the end, use one point that gave us 0 over 0. That's undefined, not helpful. In this case, something slightly different happens, even though it's still a delta x going to 0. On each of these rectangles, we're calculating the area, and our length is going to be given by the function our length is going to be given by the function, but we're going to pick a particular value of the function. So our area is going to be length times width, because that's the only thing that we need. our length is going to be the function evaluated at some points. And so I'm going to subscript it. I can write f at x sub I. This blue is bugging me. When I write x sub I, that I is an index. So I'm setting up an x1, x2, x3, x4, x5. That's the whole point of this exercise, to take our continuous and drop it back down to a discrete set. Instead of this continuum of x's, I'm just going to pick a bunch of them, x1, x2, x3, x4, and x5. And we're going to do length and multiply that by the width, which is delta x. These are just getting multiplied. By splitting these up, we get a place to put the plus signs. And so we're just going to add them up. So here, this is us adding up all the rectangles. And then we're going to do the calculus thing, let the number of rectangles go to infinity. So we're adding up all these length times width. The weird thing that's going on here is that as the number of rectangles increases, the width of each rectangle gets closer to 0. So we can't just say there's an infinite number of rectangles and they all have a width of 0. The width is just infinitely small, but not 0. Because otherwise I'd have length times 0 and they'd just be 0. But clearly there is some area there. So this is our setup for the Riemann sum. This is what all these symbols mean in the Riemann sum. F at xi. The subscript part is important because that indicates that we're indexing. We're going from a continuum of x's to a discrete set of x's. That gives us that allows us to use multiplication for each of the rectangles. That gives us a place to put the plus signs. And then we apply calculus thinking and say, use an infinite number of rectangles. They become infinitely thin, but not 0. So when people be like, oh, 1 divided by 0 is just infinity, it isn't. Because otherwise there would be 0 area here. So clearly that type of thinking breaks down. That's not how infinity works. Go take a calculus class. The important thing that we know, the big deal, is that this becomes the definite integral. So that would be the end of video 3. We get the notation. It's just a video about the notation. The next part, stay tuned for the next part where we look at reading this definite integral business. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day and thanks for playing.